Hello and welcome. I'm Haibin Zhao from Karlsruhe Institute of Technology in Germany. Today I will be presenting the power-aware training for energy-efficient printed neuromorphic circuits. This is a collaborative work with Priyanjana Paul, Michael Havenbrock, Michael Beigel, and Mehdi Tahoui. The presentation will start with an overview of the printed electronics, the printed neuromorphic circuits, and following that, we will dive into the power-aware training and the corresponding experiments, and finally, we will conclude this work. When we take a look at the electronic product, we can observe two distinct flavors. On the one side, traditional electronics exhibits high performance and they are typically designed for resource-intensive and general-purpose scenarios. In contrast, the rise of the Internet of Things has intensified the need of such computational desert, where computing tasks are generally simple and the available resources like power are often limited. Also, they are usually highly specified for certain target applications. And additionally, in those scenarios, electronics are required to be like deposable, flexible, and degradable. Apart from the aforementioned features, emerging electronics necessitate sometimes also ultra-low manufacturing costs, like in the smart packaging and smart labels. Evidently, even the most cost-effective silicon-based electronics can hardly match such low cost sometimes even in substance. To address this problem, one of the most promising fabrication methods is the printed electronics, which is a maskless and fully additive process. Therefore, the resulting printed devices can be at an extremely low cost, and additionally, by choosing appropriate materials for substrates and functional inks, printed devices can be also flexible, scratchable, porous, non-toxic, and biocompatible. In this work, we utilize N-type inorganic electrolyte-gated transistors with indium tin oxide for signal routing, indium oxide as semiconductor, and the composite solid polymer electrolyte as the gate insulator. The top gate is composed by the P.PSS. Differing from the organic EGTs, the N-type inorganic EGT generally operates below 1.5 volt and in 100 to 1000 Hz. This aligns well with the requirement of the electronics in IoT scenarios. To handle some initial computing tasks, printed neuromorphic circuits becomes favored as they can implement equivalent computational operations as in the artificial neural networks through simple structured circuit primitives. These simple structured circuits are favorable in terms of circuit design, optimization, and manufacturing. This figure illustrates a printed neuron where the resistor crossbar array serves to implement the weighted sum operation as in the artificial neural networks. Taking the first row as an example, the output voltage Vz1 can be expressed by this formula. It can be seen that Vz1 is the weighted sum of the input voltages with the weights encoded by the ratio of the conductances. Therefore, by designing and printing appropriate conductances, desired weighted sum of behavior can be implemented. Following the crossbar, an inverter-based 10H-like circuit is printed as the activation function. Its characteristic curve can be expressed by a 10H-like function. And here, the auxiliary parameter eta A is determined by the physical quantities Qn in the circuit, namely R1, R2, and T1, T2. Analogously, by changing the physical quantities Qa in this circuit, the shape of the characteristic curve will be changed. Also, it is notable that some input voltages are connected with blue circuit, which is an inverter-based negative weight circuit. Since the weights in the crossbar array can only be positive, negative weight circuits are employed to invert the input voltage into negative ones for emulating the multiplication with negative weights. Similar as the printed 10H-like circuit, the characteristic curve of the circuit can be described as a negative 10H function, where eta n is determined by the physical quantities Qn. Also, by tuning the physical quantities Qn, the shape of the negative weight function can be changed. To design suitable values in the printed neuromorphic circuits, namely the resistors, the transistors, and also to determine whether the input voltage should be inverted, we developed a machine learning-based optimization framework. In the machine learning framework, the printed neuron is modeled by this formula, where the weight W is given by this formula. It is derived from the formula from the previous slide. Here, the theta is the learnable surrogate conductance. Different from the printed conductance, theta can be both positive and negative. It encodes the printable conductance by its absolute value, which is always positive, and its sign denotes whether the input voltage should be inverted. In addition to the learnable conductances, the shape of the printed 10H-like function can also be optimized through the learnable physical quantity Qa, and similarly, the shape of the negative weight function can also be learned through Qn. In summary, the computing graph of the machine learning-based optimization model is shown in this figure. However, the target application of the printed neuromorphic circuits are generally in edge scenarios such as smart packaging, smart bandages, or smart labels. And their power is supplied generally by their initial printed batteries or energy harvesters. Therefore, to reduce the power consumption of the printed neuromorphic circuits becomes important, and thus this work focuses on the low-power design of the printed neuromorphic circuits. To this end, we developed a differentiable and precise power consumption model and integrate the developed model into the training objective of the printed neuromorphic circuits. Regarding the power of the resistor crossbar, it is easy to establish an analytical power consumption model by accumulating the power of each single resistor. The resulting power model is given by this formula. With this formula, we can now involve the power of the crossbar into the optimization objective. Regarding the nonlinear circuit, due to the circuit complexity, it is challenging to derive an analytical power model from the physical quantities Q. Therefore, we utilize an artificial neural network as the surrogate power consumption model to precisely estimate the power of the circuit. Note that these networks are not the one used for optimizing the whole printed neuromorphic circuits, but just serve as an estimation of the circuit power. To train the surrogate power model, we sampled 10,000 physical quantities Qa and Qn through quasi-Monte Carlo method, and then we conducted SPICE simulation to obtain their corresponding power consumption P. Finally, we trained neural networks to map the power P from the physical quantities Q. And by now, we are able to also include the power of the nonlinear circuits into the training objective of the printed neuromorphic circuits. This figure shows the effectiveness of the surrogate power consumption model, where the x-axis denotes the power from the SPICE simulation, whereas the y-axis represents the estimated power from the surrogate model. It is evident that the surrogate model yields precise predictions without overfitting on the training data. Subsequently, the overall power of the nonlinear circuits is represented by this formula where N denotes the device counts of the printed 10H-like circuits and the negative weight circuits. However, we observed that the power reduction is not solely dependent on decreasing the power of the circuits themselves. It also relies on reducing the number of the circuit primitives N. For instance, since none of the weights in the first column are negative, one negative weight circuit can be eliminated. Unfortunately, the device count is a discrete variable which is calculated by this formula, in which the indicator function is a piecewise constant function which provides only meaningless gradient information, as shown by the blue function. Hence, the gradient-based training process are unable to be aware of the device counts N. To overcome this problem, we employ a manual function to generate a heuristic gradient to guide the training, which is represented by the orange curve. We refer to this device count as the soft count. In this work, we employ the sigmoid function as a gradient heuristic. Subsequently, we conducted experiment to investigate the efficiency of the proposed method. In the experiment, the training objective combines both cross-entropy loss for classification accuracy and the power of the neuromorphic circuit. Here, alpha represents the trade-off between classification accuracy and the power consumption. We applied the algorithms to 13 benchmark datasets and selected 100 different alpha values between 0 and 1. As a baseline, we considered the case where alpha equals 0, which is same as the previous power unaware training works. Our evaluation matrices primarily include the classification accuracy and the power consumption. Notably, we normalized these matrices against the baseline because the change of the values are more informative than their specific values. Also, we averaged the values across all the datasets to obtain a comprehensive effectiveness of our method across different scenarios. The results indicate that with increasing alpha, both classification accuracy and the power consumption reduce. Additionally, the power decreases faster than that of the accuracy, which facilitates the better trade-off between accuracy and power. To identify the optimal trade-offs, we plotted the power versus accuracy and draw the Pareto front for all the experiments. All the points on this Pareto front represent the optimal trade-offs between accuracies and powers. Illustratively, some points on the Pareto front are listed in this table, demonstrating potential power saving with acceptable accuracy loss. For example, if a 5% accuracy loss compared to the baseline accuracy is acceptable, 50% of the power can be reduced. And if 10% accuracy loss is acceptable, it can save 60% of the power. In conclusion, printed electronics offers advantages complementary to traditional silicon-based electronics, and among printed electronics, printed neuromorphic circuits becomes particularly attractive as they implement functionalities of the artificial neural networks through simple structured circuit primitives. This benefits the circuit design, optimization, and manufacturing, and in this work, we focus on the low-power design of the printed neuromorphic circuits. By developing the precise power consumption model for the circuit primitives and by proposing the soft count of the circuit devices, we enable the gradient-based power-aware training for printed neuromorphic circuits, and with this approach, the power can be saved by, for example, 50% with only 5% loss in the accuracy. Thank you for your attention.